Hi everyone, and thank you for joining the third edition of the REXA webinar series. Today's topic is Turbine Bypass Optimization. Our presenter is Rich Rochford, Power Industry Manager for REXA. This is a recorded webinar, so if you have any questions for Rich, he'll be providing his email at the end of the presentation. With that, Rich, please go right ahead.
Well, thank you everyone for taking the time to join Ryan and me on our third webinar to discuss turbine bypass system optimization and how REXA can improve the performance of these valves at your plant. My name is Rich Rochford. I handle the power industry for REXA, and I'm pleased to have the opportunity to introduce our technology to you. For some of you attending, you may have experience with our product, so parts of this presentation will be a great refresher. For those new and looking to gain a better understanding of the technology, I am confident you will find the webinar to be informative and gain valuable insight on REXA. So let's begin. For the webinar agenda, the topics we'll be going over include actuator types. To better understand the REXA technology, we need to look at other types of actuation to distinguish them from what we do. A brief history of REXA. It was from the need to combine the benefits from each type of actuation technology that REXA originates and eventually took shape. A review of electraulic technology. We'll look at the inner workings of the REXA actuator and what makes us the most unique technology on the market. Bypass valve requirements. In order for a plant to operate as efficiently and economically as possible, it's important that bypass valves perform to a very high level. We'll touch on a number of those requirements. System benefits. You'll see some REXA installs on turbine bypass valves, and we'll talk about how they improve plant performance and efficiency. And finally, we'll wrap up the webinar with some takeaways. There are three types of actuator technologies: pneumatic, electromechanical, and hydraulic. Each uses a different method to develop forces and create motion, all with advantages and disadvantages. First, pneumatic actuators normally come installed on bypass valves in a competitive bid and are the most common in modulating applications. Their advantages include low purchase price, and they have quite fast stroking speeds. However, there are limitations of using pneumatics. With air as the compressible medium generating force, it is very susceptible to changes in air quality, the major culprit being moisture. And the air needs to build up in order to create motion. The results are losses in resolution, overshoot or undershoot, and increased dead time. Add a smart positioner into the mix, and dead time does improve, but resolution takes a big hit. Next is electromechanical actuation, most commonly found in on-off type service, which provides tighter control and better frequency response than a pneumatic actuator. However, electromechanical actuators can have limited duty cycle, usually around 25 to 30%, limited force to torque output, and very few fail-safe options available. In addition, the mechanisms involved for rotary to linear conversion are troublesome, especially in high thrust applications. Using hydraulics is the least common method to operate turbine bypass valves. These systems provide high frequency response, fast speeds with low dead time, high resolution, and fail-safe capabilities, making it ideal for operating bypass valves. These benefits, though, come at a cost. Oil volume is typically very high and requires routine oil maintenance. Most hydraulic systems are open loop and have similar types of components that includes a reservoir to draw oil from and discharge to, and filters that maintain the hydraulic fluid's optimal properties. Many issues with an HPU system can often originate from the breakdown of the hydraulic fluid. An area particularly susceptible to contamination occurs in the sump or reservoir. It's here the hydraulic fluid is exposed to the atmosphere that includes moisture and particulates. Components like servo valves are very sensitive to changes in hydraulic fluid quality. REXA combines the benefits and capabilities of each of the actuator technologies into one. The simplicity of pneumatics, compact installation of electromechanical, and the fast, high-resolution, high-duty cycle of hydraulics. How REXA came to be was from identifying control issues in a process loop and looking for methods to fix those problems. Valves were often, and still are, blamed for poor control in a process. But what if the valves were not the only reason for having control issues? Robert Glamoux from Mason-Neelan recognized that other variables were at play and had a passion to come up with a solution. He emphasized it was the final control element, the portion that controls the valves and gates, that was the area needing improvement. So it was in the early 1980s that he set out to develop a technology that had to be accurate, stable, simple, and compact. The result was the patented flow match valve technology, or FMV, also considered the heart of the REXA. From that point, the linear actuator was completed, with rotary and drive units to follow. And a little trivia, the name REXA actually stands for Robert's Expert Actuator. Okay, let's talk about some benefits of the electraulic actuator. To start with, it's a very unique design, unlike anything on the market today. The true closed-loop hydraulic system is hermetically sealed with oil volumes approximately 95% less than those found in a standard HPU. There are no filters or oil changes required, making it very maintenance-friendly. All models are 100% duty cycled through the use of brushless stepper or servo motors. These units are high precision and repeatable to 0.05% of span. Our modular design allows for very high thrust and torque output with high-speed fail-safe options. Operating temperature range is -40 to 250 F without performance degradation. And having passed rigorous testing for the U.S. Navy, REXA actuators are unmatched when it comes to being rugged and reliable. The electraulic technology consists of two primary components, the mechanical subassembly and the electrical subassembly. The mechanical portion is attached to the driven device, which in this case would be the turbine bypass valve. The electrical subassembly is basically the positioner for the actuator. This is where the main power supply and control signal are routed, and the origination of the 4 to 20 milliamp position feedback for connection to the DCS or other control system. We separate the electric and mechanical subassemblies for ease of access and operation. There are many severe applications, for example in mining and desert environments, where onboard electronics simply would not survive. The control box can be mounted in a convenient location to the valve or up to 700 feet away. Okay, let's take a closer look at the REXA hydraulic circuit. This is the real area of differentiation with our technology in comparison to HPU-based electrohydraulic systems. The centerpiece of the electraulic circuit is our bidirectional gear pump, which is coupled to the REXA brushless motor. The gear pump works in conjunction with the flow match valve, which is designated as FMV1 and FMV2 on the schematic. It is important to note, from a size perspective, the flow match valve and the gear pump can each be held in the palm of your hand. During operation, when the actuator is at the desired position, spring-loaded ball checks are locked in place to prevent the flow of oil through the flow match valve. But when there's a signal change, the motor activates, turning the bidirectional gear pump, which instantaneously builds pressure, allowing the ball checks to open. The oil is then transferred through the flow match valve from one side of the cylinder to the other. Once the actuator has reached its desired set point, the motor stops and the ball checks are seated, stopping the flow of oil through the system. Now in the standby mode, power draw is only about 50 watts. The motors are brushless stepper or servo motor style, designed for 100% duty cycle and capable of very high frequency response, greater than 4 Hertz. The cylinders that we use are dual rod, so the oil volume exiting one side of the cylinder is equal to the volume entering the other side. The design eliminates both the requirement for an external reservoir and the need for continuously circulating oil through the system. This also leads us to another significant benefit of our technology: greatly reduced oil volumes. The small REXA system, something that would require a smaller cylinder for lower thrust output and shorter stroke length, something like a desuperheater spray valve application, may only have a total of 8 to 10 ounces of oil in the entire hydraulic circuit, including cylinder. A larger REXA circuit, one with higher thrust or output and longer stroke requirements, like one driving an HP bypass valve, may have as much as 1 to 2 gallons of oil total in the system. But this is a far cry from typical control oil systems, which could have 50 gallons to several hundred gallons of oil in the entire system. Now that you're all experts on how the REXA works, let's move into some background on turbine bypass systems. Of course, their primary purpose in life is to direct steam around the turbine during startup, shutdown, and trip events. But these days, with a reduction in power demand, plants are more frequently cycled, causing bypass valves to operate in low load and simple cycle operations. And for plants with multiple combustion turbine generators, heat recovery steam generators, and a single steam turbine, for example, a 2x2x1, the bypass system also allows staggered startup of the combustion turbines. A common arrangement found in a combined cycle power plant is a cascade bypass system with a triple pressure cycle and includes HP, hot reheat, and LP bypass valves. This next slide shows a simple schematic of the system. HP bypass steam is directed to the cold reheat line on the exhaust side of the HP turbine. It's mixed with IP steam, reheated, then directed through the hot reheat valve to the condenser. The LP bypass valve, which is not shown here, is tied in just before the LP turbine. It protects the condenser by reducing reheat steam pressure and temperature to an acceptable exhaust condition. The ability to precisely track control signals can prevent adverse effects on the HRSG and turbine, such as thermal and mechanical fatigue, gas turbine trips, and safety valve trips. Typical characteristics of a bypass valve are stroke ranges of 6 to 12 inches with 10 to 30,000 pounds thrust required. Standard issue for these valves in normal operation is a less than 5-second stroke time in both directions and trip speeds in 1 to 2 seconds. Valves must be stable, have a high frequency response, meaning able to move with small signal changes, and be repeatable. A key to improved heat rate is tight shutoff when closed, and valves must remain closed on loss of power. And speaking of control signal tracking, this next slide is a snapshot of actual test results showing the accuracy of the REXA actuator compared to pneumatics. With deadband set at 0.1%, which leads to a resolution of less than 0.1%, and linearity capable of 0.05%, the REXA X-Pack is the only actuator product line truly capable of matching the potential of modern control systems. Now, if these requirements are not met, this leads to a number of problems such as delayed startup times, reduced generation, and increased offline fuel usage. This can be a significant cost to the plant. Leaking bypass valves decrease turbine efficiency and increases overall heat rate as more steam is needed for required output. Poor control of the hot reheat valve, which is basically the heart of the system, leads to overactive spray valves, cascading down to fluctuations of the IP drum level, and continual compensation by the feed water valve. So as you see, instability of all related equipment occurs, creating a very nervous control room. Lack of control of the HP and hot reheat valves can also lead to increased HP turbine exhaust temperature and potential windage overheating of the HP turbine back end, causing efficiency loss. Okay, now it's time to look at some REXA installs and how we were able to improve plant performance. The first slide shows an HP bypass valve at a public service electric and gas plant. We were advised of two big issues with the original pneumatic actuators. Valve positioning was not repeatable, leading to very poor HP steam pressure and temperature control. The second and equally important complaint was that the valves leaked almost immediately after rebuild, substantially increasing maintenance cost and heat rate due to bypass steam. The high resolution of the REXA actuator gave plant operators predictable valve performance and long-term tight shutoff due to our hydraulic circuit flow match valves locking the actuator in place. You know, a funny thing happens after a customer installs one REXA actuator on a critical service valve at their plant, and it does exactly what we say it'll do. The customer starts looking themselves for another place to put one. The next two slides are before and after pics of hot reheat valves at the same plant. The pneumatic piston actuators were not able to overcome binding with the plug-in cage when open and rapidly heated. This is caused by significant differences in body versus trim mass. What happens is the trim heats up much faster than the body and expands first, finding the plug inside the cage. The result was erratic performance and reported jumping of the valve plugs, causing horrible instability during every startup and very nervous operators. And consequently, the trim in these valves was being rebuilt every year. Once the REXAs were installed, plant operations immediately noticed smooth stroking of the valves under all conditions, settling down all related equipment. This is due to the REXA high frequency response, the incompressible nature of hydraulic fluid, and our actuator thrust output unaffected by outside influence up to max rating. Also, this was another set of valves needing yearly trim rebuilds. Since install approximately 2 years ago, there has been no maintenance performed on any of these valves. This next installation is a New York Power Authority plant. Due to the pneumatic actuator instability between 30 and 60% of stroke, plant efficiency suffered and desired startup times could not be met. Overshooting of the control set point was a major problem. After the REXA installation, startup time was reduced by more than half, which increased plant efficiency. And control was greatly improved due to our virtually instantaneous frequency response to control signal changes, zero dead time, and no overshoot. Next, an HP bypass valve is shown with before and after pics. There were two issues with the hydraulic actuator at this plant. One was the high maintenance required for the HPU. We haven't talked too much about straight hydraulic systems today, as they're not as common as pneumatic installations. But oil contamination and breakdown can be a huge problem, plugging up small ports in servo valves, causing erratic actuator operation. The other complaint was the fire quill hydraulic fluid itself. It's mandated at many plants due to the fire-resistant qualities, but it is hazardous to both personnel and the environment. With this in mind, the plant was anxious to replace as much of the hydraulic system as possible. Though not shown, the IP and LP bypass actuators were replaced, along with the associated spray valve actuators for the steam conditioning portion of the units. At a TOSHIBA plant in Thailand, another electro-hydraulic actuator manufacturer in Japan won the initial bid with a valve company due to cost for the HP and LP bypass valve actuators. These very large units were unable to control accurately during ramp up and ramp down and extended these times more than 20 minutes each. This had an impact on plant operations and online time. After 5 service calls by the manufacturer during the warranty period, the end user was convinced that REXA was the answer and replaced all of these actuators. There have been no reported issues since installation. This last example shows a REXA actuator installed on a turbine bypass valve for a new topping turbine at a pulp mill in Canada. This turbine was installed at the plant to handle the main steam pressure reduction from a 1,500-pound recovery boiler to a 600-pound process steam line. The original bypass was a CCI drag valve with pneumatic piston operator. The reported problem was very unstable control when the turbine went into a load shed or trip condition. The pneumatic actuator was fast to respond, but would overshoot due to the rapid response, causing instability in the process line, ultimately leading to a trip. The impact to the plant for losing this steam line was greater than $100,000 per hour in production. REXA was brought into the project, known for speed of response and stability and control, and a 20,000-pound REXA actuator was installed with full 6-inch stroke either direction in 1 second. The unit immediately paid for itself 5 times over on the first trip event that was eliminated. The REXA advantage and key takeaways. Let's face it, decreasing ramp times means offline fuel savings and more megawatt hours to the grid. REXA has been known to improve these times by as much as 25%. There are many things that come into play when a steam turbine trips. With our tight control, we have been able to catch those pressure swings and alleviate trip events. This is especially noticeable in units with small steam drums. As shown previously in a number of the installs, tight shutoff from our hydraulic lock-in-place feature is key to maintaining seat tightness and reduced erosion. The cascading effect causing other equipment to be overactive, increased required maintenance, is also greatly reduced. In plants with multiple hot reheat valves, a predictable startup is important. The opening of these valves are staggered, so with an almost instantaneous movement of the REXA actuator to control signal changes and no overshoot, the transition is smooth with minimal impact to other equipment in the system. And lastly, due to the fact that the hermetically sealed and pressurized hydraulic circuit is not exposed to the environment causing contamination, the oil never has to be cleaned or changed. With a minimal number of seals and a small makeup reservoir, any weeping due to temperature change is compensated. And since the electronics are separated from the actuator and away from a potentially harsh environment, life is considerably extended. A REXA actuator is not a product, but a solution that will make the difference for your plant on critical applications such as turbine bypass valves. It's a sound engineering decision and an investment that will continue to carry forward. Thank you all for joining in on this webinar series on turbine bypass system optimization. Please feel free to contact me anytime and I'll be glad to assist you.